Hi, this video is about harmonic frequencies in closed pipes or air columns. So we've seen in previous videos that harmonic frequencies exist on strings and on open pipes. We're going to add one more type of harmonic frequencies we often see in nature, and this one's a little bit different. And you can already see that here if you're looking at the pattern that you see. Excuse me. So a closed pipe would be any kind of, air column or tube or pipe where one end is capped off and the other one is left open to the atmosphere or the air. So in this kind of situation, we have always on the end that's capped off or closed, we have a node. A node is a part of a standing wave where there is no displacement. And because this part is closed, there's not going to be any room for displacement of the air molecules in this part of the pipe. At the other end, we have an antinode. We are at the other end of the standing wave, and this is the part where there's maximum displacement. Because these are the requirements, these are the constraints for what kinds of waves are possible inside of a closed pipe, we only have certain frequencies or wavelengths that are allowed to exist in a closed pipe. And they follow this pattern where this first one goes from a node to an antinode. This would be only 1/4 of a wave. If you think about a wave as being, one full cycle going up and then back down, we're missing a lot of the wave here. It's just 1/4 of a wave. And then for our next wave, we do have a little bit more of the wave, but it's still not quite a full wave because we're starting here at the node in the middle. We go up for a full crest and then we get halfway through a trough. And so this would be 3/4 of a wave. And then finally we keep going here. Same deal. We end up with a full wave plus an extra fourth here. So that's 5/4 of a wave. So this pattern, because it's a node on one end and an antinode on the other and they're different, we only are allowed to have odd numbered harmonics. There's no second harmonic here. There's no fourth harmonic. It's only first, third, fifth, and so on. So for this kind of relationship, when we write it out mathematically, we have a different way of writing it compared to the other two types that we've seen so far. So we say the length of the pipe is any number of fourth wavelengths, except that n can only be odd numbers. So that's kind of the way that we write that. So we can put a box around it like this. And then the frequencies that are possible, likewise, have to do with this pattern of only being odd numbers of fourth wavelengths. So we have this equation for the frequencies. Excuse me. So knowing this, let's go and look at a problem and try to solve a word problem involving this. So one of the ways that you can have a closed pipe is when you have a soda bottle that you blow over the top of. I think of this example a lot. So we have here a bored student blows air across the top of a plastic soda bottle, which creates a complex sound within the bottle. And it says the fifth harmonic frequency of the wave here in this closed-end air column is 2600 hertz. Assuming the speed of sound in air is 343 meters per second, what is, or how tall is the air column between the top of the lid and the surface of the liquid? So we have some amount of liquid in this bottle, and we have, what we really want to know is what is the distance between the top of the lid here and the surface of the liquid. That's what we're asked to find. And this just also happens to be the length of the air column before it turns into this, liquid surface here. This is the length of the air column. So this is the capital L that we're trying to find. And we are told that this is the fifth harmonic, n equals 5. And the frequency of the fifth harmonic, F5, is 2600 hertz. So it also tells us the speed of sound in air, we're going to see this number pretty frequently, is 343 meters per second. So we're looking for this length of the air column here. So when you're doing this kind of problem, just be careful and remember that this equation for closed pipes looks a little bit different than the equations for open pipes and strings, because we have this 4 down here in the denominator instead of a 2. So I'm going to put in my values here. We have 2600 hertz equals 5 times 343 meters per second divided by 4 times L. So I'm going to be doing this math real quick over here. I'm going to multiply the numerator first. So 5 times 343 is 1715 meters per second over 4 times the length. And this is 2600 hertz over here. Now to get this denominator out of the, to get this L out of the denominator, to get it out of this fraction, I'm going to multiply both sides by L. And then I'm also I want to get rid of this 2600 over here. I don't want this to stay, so I'm going to end up dividing this side by 2600 hertz. So I'm going to do that to both sides. What that essentially does is it swaps the place of this L with this 2600. So this is my super secret math trick that I often do. So rewriting this just to make it a little bit more clear, hopefully, we have 1715 meters per second divided by 4 times 2600 hertz. So this is going to be the length of our air column here. And doing this math will give us 0.165 meters. So about 16 centimeters or 17 centimeters rounded to two significant figures there. That makes sense for like a soda bottle. It's not too big of a gap here between the top and the liquid. So yeah, that's how we deal with these kinds of problems. There are, of course, other ways that you'll need to work this out, maybe solving for the frequency or the speed, but this gives you the general idea for how to use this closed end pipe. So that's all I've got for you in this video. Remember, the opposite of love is not hate, but apathy.